Good afternoon, everybody. Welcome to the next session. We're going to learn how to stop leaks today. Okay. Thanks for that, Steve.
Steve, we actually talk about it in here too. I got you.
Well, let's see if that's going to...
All right. So I'm Matt Archibald from Invent. So yeah, I guess we'll flip over to that. We're going to talk about the risk and reward with liquid cooling, what some areas that liquid cooling can enable. I'll probably reference a few of the earlier sessions today from the various work streams and projects. I've got Fred Rebarber here from Vertiv as well to help work through this and go over. And I guess, yeah, we'll just sort of show where this came from.
Show of hands, how many have read the white paper? Okay.
And we've got a few, that's good.
Okay, good.
So if you're not, we'll give a nice synopsis or overview to the white paper, what really drove this, and give you some more encouragement to go out and read the white paper if you haven't done that. And yeah, and any more on that?
No, just a quick background on myself. So I've been with Vertiv for 16 years, and so been doing liquid cooling that whole time. Started at chip level cooling, and I thought it was happening 15 years ago, but I'm pretty sure it's happening now. But I've done a lot of liquid deployments, have seen a few leaks, and experienced some things during commissioning. So hopefully we get to share a few stories so that we can all learn from both of our experiences. But we put our heads together with a couple of other colleagues to try to document some of that as much as we could, with some good pictures. So there's a lot of pictures of the deployments in the white paper that you won't see here. So.
Yep, so just like Fred, I've probably been doing liquid cooling installations and designs for various predecessors to Invent for probably about, not as long as you, Fred, probably about 8 to 10 years. A lot of field time, a lot of experiences. All my experiences have been with positive pressure, water-based liquid type solutions. But I think on top of that, with Fred's experience and how we developed this white paper, it was a really extremely collaborative effort, pulling in various contributors from the different communities, the different work streams, from immersion, cold plate, some of the blind mate project, as well as the vendors that we have listed up here, down to the chip level with Intel contributing, Cool IT. Cam Turner couldn't be here due to COVID restrictions, but Vertiv and Invent as well. And Nigel Gore, who's probably headed up this paper from Vertiv as well, couldn't come from the UK. So it was a very collaborative effort. There's a lot of case study that went into this. As Fred said, there's a lot of pictures in this, different deployments, whether it's refrigerant, whether it is positive pressure with liquids, dealing with dielectrics and things like that. And all the concerns, and Steve just walked out from Childine, so we do talk about negative pressure and the effects that have there. So we'll jump right into it and sort of get into why, what was our motivation, what was our drive behind this, and it was really, there's a lot of different technologies out there from the service liquids that are used, the challenges that are there, the different deployment scenarios. And it's not that we're trying to, say this is the way to do it, but it's to get some level of alignment on how to assess whether you go liquid cooling. As Fred says, we've been hearing for years that it's going to be here, it's here now, and I think we're really at the point where it's really here.
Yeah.
Some of the other conversations have said with these chip power package densities continuing to go up and overall server package densities going up, it really is the here is now. So we wanted to lay out some concerns with the different technologies and go over not only how to prevent leaks from a design perspective, what's important, but also if a leak is detected, the different technologies that showcase that, and then what to do determining where a leak is detected.
Yeah, in the paper we also look at refrigerant as a fluid. I've done a lot of work in the refrigerant delivery area, so I think that's going to be helpful as you go through that. And a lot of the focus has been on the fluid types and some of the different techniques that are used. So it's both direct and indirect on the detection. So I want to make some distinctions there as we go through the paper.
Yeah, so, as we sort of gave a little bit of foreshadowing to this, we generally make the statement that in a lot of cases, liquid's already been present in the data center for a long time. Now what we're doing is we're really talking about bringing it closer and closer to the IT. Rear doors have been out in the industry for a while. That got liquid very close to the IT equipment, but cold plates is as one form of liquid, whether it's water-based or whether it's a refrigerant or something like that. It's actually going within the server, and there are challenges with that. There are risks associated with that, but there's also a lot of rewards. Others that you've seen a lot of the solutions in the expo hall around immersion, that is immersing in liquid, and it's a non-conductive liquid, so hey, there wouldn't be a problem if there's a leak, but there's other, we'll call it human error problems and things like that to be aware of. So we'll cover, as Fred said, that some indirect methods of leak detection, some direct methods of leak detection, cover some of the rewards that you get by enabling liquid cooling. We're not going to go into a whole lot of depth, but mention it at a high level. There was a unique chart put up in the Microsoft presentation this morning on their immersion cooling journey that just shows what some of those technologies can enable in terms of performance and how they balance that. And we've highlighted those issues or those rewards here going forward.
We had some great debate when we were writing the paper, and it was about, how much intervention do you take once you find a leak. And first you got to verify that it really is a leak, right, and not condensation of some type. So there's some things that we offer in the paper to think about as you design the system. But if you just follow the liquid all the way from the chip all the way out, and this is through the any crawl units that are in the place, the CDUs all the way out on the piping, the trays up in the overhead if it's overhead or down below. So we try to follow that path and offer a way to detect, but really concentrated on where to focus to put the leak detection, so that you can make an educated decision on what action to take. And I think that's where we all would debate is do you shut down the server node? Do you shut down the rack? Do you shut down the row of racks? Once you make the decision to shut down the CDU, then you have kind of isolated what could be a big portion of it.
Yep. So we'll talk with some of the terms that we're going to use briefly through this and that are used throughout the white paper. Really, it's sort of a bit self-explanatory, but for clarification, detection is detecting the leak event. It can be at various different points throughout the fluid network, as Fred described. The next one is mitigation. Is what do you do when to prevent a leak? How do you go through those design choices? How do you go through those deployment scenarios to prevent that and mitigate leaks from happening? And with some points of importance there. Another one is, okay, so a leak was detected in various different systems. What do you do? That's the intervention piece of it. And then the difference, as we mentioned before, is we sort of boiled it down into two different things: is a conductive fluid or conductive medium and a non-conductive fluid or medium. Typically, your conductive fluid is going to be a water-based type of coolant. You can use direct conductive sensors to detect that, and then a non-conductive, either, we refer to it in the paper as dielectric, but it does include refrigerants. That's definitely a non-conductive leak that has various different issues to factor in.
Yeah, on the refrigerant side of things, where I've seen some of the leaks in the systems is definitely at the couplings. It's interesting, sometimes the leak comes as a question from the customer. It says, it seems like my cooling capacity has gone down. Yep. And so we'll go in, and usually it's more of an indirect method, but you can go check the sight glasses on the inside of the CDUs and see where that fluid sits in there. And so when you're doing refrigerant, it's a little different because you're trying to snip around on the lines, but the connections are ones. And in a lot of cases, sometimes it could be a torque issue on the particular connector and how that's applied. So in refrigerant systems, and we'll work to get more precise as we go. And I think hopefully over the next a few years, as the chip densities gets up, you may see refrigerant make a resurgence back to the chip level. So all the learnings that we've had, through the last few years will apply. Yeah,
and I think that really, illustrates the system design aspect. As you said, with a refrigerant base, you're not using a conductive means of sensing leaks, but there are different tools depending on the different fluids used, and same with dielectrics. And when you factor in two-phase dielectrics where you have that phase change, that's another one. So level sensors, leak detection ropes for conductive mediums and things like that, monitoring those levels, even down to things like we talked about yesterday was turbidity sensors. And they're not just limited to refrigerant base where you're measuring any gaseous in the water or in the refrigerant, but you can measure the gaseous or any contamination levels in the water with that, with certain turbidity sensors. So there's a lot of different products that spill over, and it all looks back into the sort of the wider, maybe spills into the ACF, and they're not quite there yet or what, but the overall system design for where this liquid loop's going to go, if you're isolated to a CDU for your secondary and it's localized, or it's a facility level CDU, these are all sort of the considerations that you have to deal with. That the paper goes into detail about the trade-offs of each, the applications of each, and the benefits of each.
Yeah, and understanding how that information flow goes is, so these leak detection ropes that are in these examples here are tied back to the BMS system in many cases, the building monitoring system. So your technicians can get advance notices. In the top picture, that was actually rope that was put under a rear door. And so we could actually know which door position we had an issue. And then the other rope is in the bottom of a CDU. So both of those lines actually fed back through the BMS. The one in the CDU fed through the connections in the controller, and the other one was a point tied back to through Modbus through a relay.
Yep. And I think that's a really good transition into, so we've detected a leak, we've come up with some design considerations around couplings. A lot of the connector vendors, go to great lengths and have a lot of reliability data on fatiguing and things like that, and to avoid those leaks at those points. The previous session that was in here from ACS or ACF, they're spending a lot of time talking about connections. I think that's the next session in here is actually the panel on facility connections. So we can detect leaks at all those potential leak points throughout, but then it gets into what you highlighted, Fred, is intervention. Okay, so we've detected a leak, what do we do now? And depending where you're at in that loop, a number of different things can happen. I think it's really, for this audience at OCP, it's really key to say, it is about uptime, but it's also about balancing scale. So it's one thing that I've detected a leak, along my facility pipe. Is that necessarily a problem that requires immediate shutdown of the IT? Maybe, maybe not. But detecting a leak at the facility level and detecting a leak on following a cold plate loop within a server is, those are two different things that you probably want to take action with different response times. So we do talk about that. We go into depth. It's a leak is a leak, and they're all severe. But it's what should be the actual intervention action. How is that handled? How do you go about assigning that hierarchy and priority? So a lot of that factoring into, which BMCs are alerted, where those BMCs are alerted, and then, for me, it's about uptime, whether it's VMs, microservices, or something like that. It's about transitioning workload before that IT goes down offline to remedy the problem, and you're still maintaining capacity. It's not just an unknown outage and you're done.
Yeah, within the paper, we offer a couple of tables that actually say whether we describe a leak, and then we describe the severity of it. And of course, we were pretty general about moderate, low, or high, and then some actions that could possibly be or should be possibly taken. And if you do have your leak detection network through the whole data center, that could give you multiple points of information. So if you find one at a node in the server and that leak is also appearing at the base of the rack or near the rack, then you've got something that might actually need immediate attention.
Yep.
If you've got multiple points.
So then we get into the fun parts about dielectric, because that's a really interesting, I'd say, problem to solve. I like weird things, but when you have a non-conductive medium in there, that could be either single phase or two phase, there's a whole different set of how do you do leak detection, how do you manage that, and how that can be done. And we do have indirect leak detection methods, we have direct leak detection methods, and as we talked about with refrigerant, which at atmospheric will change phase. That'll escape as a gas, and that's a different problem to deal with. So you're limited with non-conductive medium because you want your dielectric to be non-conductive, or your refrigerant. You're looking at really differential pressures, turbidity, level sensors in reservoirs and things like that to really tell you if you have your cooling medium escaping your loop. We'll call it closed loop system. So there can be difference in differential pressure over time, and you have to be able to have the algorithms or the logic in place to determine if nodes were taken out of the loop, and that's going to affect the differential pressure. Racks were added to the loop or turned off from the loop, and that parallel pressure changes, and all those things, and monitoring that. And as Fred said, probably one of the biggest things is when there's a leak and things aren't running to the design point, you'll see a heat rejection capacity reduction. And it's being able to monitor that and say, well, did nodes come offline? Is the workload just low? Or do I actually have a deficiency in my cooling loop that I need to investigate further? So for a lot of those pieces, we actually went into the ACS immersion work stream. They were sort of the first work stream to set down some guidelines around requirements around these different types of fluids, especially with non-conductive mediums. So we did with this paper borrow from a lot of different things and build on that and try and bring a lot of the work streams together and say there's a common theme through all that, and how to deal with that.
Yeah, and I will also add, I don't think we touch it on these slides, but the paper does cover some other leak potentials where you might have a leak from a earthquake.
Yeah.
Right? If you have a rupture on a pipe or something like that, and what action can you take there? We also talk about what if there's spillage on the floor. It's actually a safety slipping hazard.
Yep.
Some of those ancillary things that you don't think about that leaks could cause, the first thing you're thinking about, oh, I'm losing cooling. But you also have to think safety as well, especially with refrigerants, because the refrigerants will displace oxygen. So, depending on the size of that data center, you might have to have oxygen sensors or some kind of refrigerant evacuation system. But we also, in the glossary in the paper, there's some great references there you should take a look at, like ASHRAE 34 and 15 to check that out.
Yeah, so we cover a lot of the risks, the system design components and things like that, and what are the rewards? Where's the motivation to go to liquid cooling? So there's been a lot of sessions that highlight this. It's a big factor in the exhibition hall. There's a lot of different liquid technologies out there. There's a lot of different liquid technologies that are being discussed in the sessions, and really it enables pushing the bounds in the overall rack power density. Servers can stay small, servers can stay dense. It enables picking up higher performance chips, processors, ASICs, GPUs, FPGAs, whatever you may be deploying out there. But it's not just about supporting higher power. It's also in a lot of those ASICs or processors, it's also about enabling, extended turbo mode or extended performance boost modes. It's enabling overclocking for extended periods of time. An air-cooled processor would probably be called turbo, but an air-cooled processor would probably give you about 2 seconds of turbo before it has to throttle back, and it's being able to take advantage of that performance or dynamically overclock the system to take advantage of that long sustained runtime and being able to better enable use of every single clock cycle that is in all those cores. Another couple of the presentations touched about, that's just on the chip level. You get into, well, what do you enable on memory and memory bandwidth and things like that, and I/O cards and storage. All of these things they're here, they're coming, and that liquid cooling on all those components enables higher performance across the board. So you get more life out of less IT. You get longer life out of the IT you do have. So that does optimize the performance, but it comes at a cost of power. But it also, you look at the liquid cooling solutions compared to air cooling solutions, and the PUE or PPUE is extremely, extremely good compared to air cooling. And these are knowns. There's a lot of drivers to that. So you do get the sustainability options, you do get the environmental options, and whenever you can shave off that cooling aspect from the facility side of the PUE equation, you're actually freeing up capacity for more IT deployment. So it does enable a lot of the capacity to start exceeding the demand curves.
And I would add that I gave a presentation earlier today on sustainability, and how liquid cooling was maybe a first step towards looking at a sustainable, maybe carbon neutral, carbon-free initiative. And that was received pretty well, because I think when you look at what liquid cooling brings to you from a sustainability, and if you're able to really leverage the power of the liquid cooling and increase your feed temperatures from your chiller, the energy savings from that piece of the equation can be significant. So I think there's some great starts towards sustainability models and getting to zero carbon there.
And I think the other nice point to build on that is that it's not one size fits all. It's not one solution is necessarily better than the rest. It's that there can be any solution that's out there for liquid cooling, and what we're sort of promoting is, and the white paper really promotes, is not just water-based liquid enablement, but any on-chip or in-server sort of liquid cooling. There's a million different ways to do it. Not a million, but there's quite a few different ways to do it, and to do it well, and to do it safe, and to do it efficiently. So yeah, what we really set as foundations from the white paper is these are complex systems, and Fred's been around them for years. I've been around them for years. I know a lot of the faces in a room. There's a lot of history of people that have worked in this space for many, many years. And if you go back 10, 15 years, it was a very specific design solution that was just fraught with complexities the whole way through. As we move forward in time, I guess it's a personal goal of mine is to make any of this liquid cooling digestible, or more digestible, more interconnected. I like where OCP is driving, and the collaboration that we've been able to have across vendors to make the products work together better, easier, but also mitigate the risks along the way and make it not such a very specific or designed solution, and allow that flexibility. So all the different iterations, we talk about that and we go through it, but then it's also, the solution design is only one part of it. You still have to build it. You have to know your vendors. You have to trust the vendors. You have to work with the vendors to make sure that solution's going to work. And then you have to work with the MEPs and the facility engineers to make sure when it goes in, it's thoroughly tested, that all the systems are operating together. A leak detection doesn't necessarily have to be directly tied into a BMC, but you want that visibility. But through testing, commissioning, and deployment, those are all factors that you have to consider with these solutions.
Yeah. After you go through the paper, I think our contact information is available. I'm happy to collaborate with the OCP community and answer any questions directly. So I think both Matt and I would love to get involved and hear what challenges you might find.
Yeah, and what we have today isn't the end of the line. It's not the end-all, be-all. The call to action is encouraged. This project came out of the ACS cold plate, but get involved in immersion if that's what your path is, or if you're looking at exploring it, get in touch with us, get in touch with the cold plate work stream. Some of the blind mate manifold work stream as well has had a lot of impact on this paper. And the next one that Fred and I are going to be presenting on the integration, there's just, at a solution design level, there's just a lot of pieces involved. So I'd say get involved, get information, ask questions. We're all here to help, but this also gives us input on where we should be looking at as infrastructure vendors. Great. So yeah, I think with that, we'll open it up for questions if there are any. But if not, thanks for your time and thanks for coming.
Yeah, thank you.
Yep.
He's coming to the mic.
Yeah.
Josh Guess at Oregon State University. Here, I'll get a little closer. I'm asking in a timely fashion. Joshua Guess at Oregon State University. What about the form factor of the connectors? Do you see that making a quantum leap, innuendo intended, I guess, on minimizing that size to accommodate the channel size of fluid delivery that we'll need to cool the heat fluxes that we expect in the next 10 years?
You want to start and then I'll add to
it?
Embedded cooling is kind of where my mind is going.
Yeah.
But, I mean, there are other channels we need to connect to before we start talking about building a brain in the chip.
Yeah. So, historically, where we've been with connectors is it's been very vendor specific. UQD and the work within OCP around a standardized connector and the other blind mate connector within within OCP are good examples of, it may not be the best solution, but it's a starting point. You know, it solved the problem that we had at the immediate. We, as an infrastructure vendor, are constantly working with a lot of the connector vendors on, you know, we'll use a connector until it creates a problem or until a customer tells us that there is a problem. Then we have to go back and say, let's make tweaks. So where we're going in terms of the form factor, we haven't been pushed, I'll say. We haven't been pushed to make something smaller, but there definitely is. They do make connectors with different bore sizes. You know, that affects your CV, either enables higher flow rates or a specific pressure drop, and all of that has to be factored in. But in terms of, you know, we'll say a blind mate connector doesn't necessarily have to be as long as the first gen that they did. Will that change in the future? Most likely. But this was the first shot. We didn't know how IT equipment was going to mate with all that and all that stuff. So next, I think we probably will be pushed to make that connector shorter, smaller, et cetera. So it's an evolutionary process, and it's only going to change if we have input from people like yourself that say, I think this is a problem, here's why, we'll make that change.
Yeah, and I'll just add that I think the connector size itself is going to be really dictated also by the amount of fluid flow that you need for the individual server node. The actual KWs of the racks that we see are kind of all over the map, but remember that that's going to really be capped also by the amount of power that you can get into the rack. So I think you've got to look at both the cooling and the power as far as the maximum KW that's going into that rack, and then that'll dictate both the connector size and the manifold size. In a lot of the solutions, cold plate solutions, you'll notice that you've got maybe 70% of that heat that's in the IT will be going into the fluid, and there still needs to be some air involved in that process potentially if you're doing a cold plate solution. So you have to consider that as you add manifolds and multiple PDUs and whips that are powering those power systems can be, you know, quite large in diameter. So there's a lot of work that you have to do to understand that piece of it. But I think the connector sizes will change in scale, but they'll be limited. Yes, next question.
Well, actually, that's all the time we have.
Okay, great. Sorry. That
We
was.
thank our speakers.
Yeah, thanks.
Thank you.
Thank you.